And welcome to another video on Norton's theorem. In this video, the goal is to find the Norton equivalent of this circuit looking through these terminals. And in order to do that, we need two components. We need I of n, that's the Norton current, and we need R of n, that is the equivalent resistance of the circuit when all the independent voltage sources have been turned off. And finding I of n is actually quite simple. We just want to how to do that. We just want to connect a short circuit across the terminals of the circuit, and the current flowing across these terminals would be the value of our I of n. We know that that is the case. Let us proceed to finding the value of I of n. We can find the value of I of n using nodal analysis, and we have three essential nodes here. We have this node, we're going to call that node 1. We have this node, we're going to call that node 2, and we have this node, I'm going to call it the reference node. So node 3 is our reference node, and if you look closely, you see that node 2 is connected directly to node 3 through I of n, so we can say that V2 is equals to 0 since it is connected directly to the reference node. So V2 is equals to 0 volts. So we're interested in finding V1 now, and to do that we write the KCL equation at this node. And we don't even need to do that. We know that V1 is 30 volts, so we can write that as V1 equals 30 volts, and this is because you have a voltage source connected across V1, so we know that V1 is 30 volts. That was easy. Now, the way to find the actual value of I of n would be to write the nodal equation, the node equation at node 2, and since we know the value of the node voltage of node 2, we can say that V2 minus V1 divided by 15 times 10 raised to the power 3 plus 5 times 10 raised to the power minus 3 plus V2 divided by 5 times 10 raised to the power 3 plus In, all equal 0. Then we can substitute in the values that we know, and would have minus 30 over 15 times 10 raised to the power 3 plus 5 times 10 raised to the power minus 3. This equals 0 plus I of n equals 0. Sorry, this should be raised to the power 3, not raised to the power minus 3. And with that, we should arrive at 3 times 10 raised to the power minus 3 plus In equals 0. And we know that In equals minus 3 times 10 raised to the power minus 3 amperes. In essence, what this is trying to tell us is that we assumed the wrong direction for our current. So instead of our current source to look like this, it will not be looking like this. It will be looking something like this if you want to assign a positive value to the current source. Next thing to do would be to turn off all these voltage and current sources and compute the value of R of n. And the circuit that we'll be using to do that will look something like this. The circuit will look like this when you when you put off all the independent power sources, replace the current sources with open circuits and the voltage sources with short circuits. Now, what we just have to do is to resolve these resistors into one resistor. Now, these two are in parallel with one another, so they cancel each other out. and with that we'll be left with two resistors that are in parallel with one another. So we can easily say that 15 raised to the power minus 1 plus 5 raised to the power minus 1 all raised to the power minus 1, and that should give you 15 over 4 ohms, which should amount to 15 over 4 kilo ohms, sorry, should amount to 3.75 kilo ohms. And we can then proceed to drawing our Thevenin Norton equivalent circuit. Our Norton equivalent circuit would look something like this. This is the direction of the power source. And we have 3.75 kilo ohms here in parallel with the power source, and we have our current source, that's 3 amperes, 3 times 10 raised to the power minus 3 amperes, and we have A, B, and this is the Norton equivalent circuit of this circuit when viewed across these terminals. Thank you for watching. Don't forget to hit the like button and subscribe. See you next time. Bye. Thank you.